Okay, good afternoon. Let's go ahead and get started. I haven't forgotten to go over the last exam, but we actually are not going to do that till Friday. I feel badly that I waited so long to do it, excuse me, but there was a particular reason they had for doing that. But I promise Friday we're going to go through the most missed questions on the last exam. So stay tuned for that. I also had a question that I thought, the more I thought about it, the more I thought, well, let's address this. So our next exam, so here's the syllabus. Okay. Our next exam right here, the 28th, is only a few days after your fall break. Okay, so somebody asked, that seems really close to fall break, can we not do it then? And to me, I think, well, it's 3 days after. I wouldn't do it on the Wednesday back. But to me, you've got a few days there, and to me, that seems reasonable. Now, I know that if you're going away on fall break, then that might be kind of difficult, but the idea is you have 2 days off to kind of rest and recharge, and then, you know, maybe start studying a little bit the week before, and to me, that should work out fine. Now, potentially, I could push this off until Monday. But if I did that, then I would also want to put the next Friday exam off to Monday, and that's the week of Thanksgiving. So I've done that in the past, and I always run into problems with people taking that whole week off. So, yeah, so that's my thinking. If you feel really strongly one way or the other, like, yeah, you really want me to change those, or yeah, you don't, then come talk to me. And I'm willing to listen to that. Maybe I need to send out a class survey or something like that. But I would rather leave it where it is, because when we get the Monday exams, a lot of students work like long hours on weekends. So I think Monday exams are not ideal. So, okay, so I would sort of rather leave it, but again, talk to me if you want to, you feel strongly about changing it, I guess. Okay, it was kind of like a challenge flag, like, okay, let's revisit this. let's do the instant replay and think about it a little bit more. But all right, so picking off where we left off last time, thinking about control mechanisms. We talked about heat, probably spent most time about that, on that. Some other methods where we're basically dehydrating cells to keep them from growing. And last, kind of the last big area in terms of physical control would be radiation. So this should look a little bit familiar, because we just got done talking about how different kinds of radiation causes mutations in our genetics chapter. Of course, ionizing radiation, that's the really shorter wavelengths here, X-rays, gamma rays, and we're also going to talk about using electron beams kind of briefly. But those wavelengths are going to create ions in cells. That essentially means they're going to pull electrons off of other molecules. So that causes a lot of damage, not just to microbes, but to us as well. So we have to be really careful if we're using this kind of radiation. But it can break DNA, both strands, even one strand or both strands. That's ionizing radiation. Oxidizes covalent bonds. Remember, covalent bonds are where electrons are shared. They're a very strong, stable bond, widespread in nature. So, you know, DNA, those phosphodiester bonds are covalent bonds. Proteins have covalent bonds. Water. Okay, so widespread. ionizing radiation can also create hydroxyl radicals, which has an unpaired electron. So again, pulling electrons off of other molecules. That was one of those toxic oxygen species that we talked about. This can be a good method to disinfect or even sterilize objects, especially if those objects are going to be susceptible to heat and you can't use heat on them. So this may be a good method if you don't want to use heat, and it can disinfect or sterilize pretty rapidly, especially when compared to non-ionizing radiation that takes a lot longer. And it penetrates a lot better, again, compared to non-ionizing radiation, which we'll talk about next. So if we look at some uses of ionizing radiation, like I said, we can use an electron beam. That's produced by a cathode ray machine. Your book really doesn't spend any time talking about this at all, so maybe it's not as useful as some other kinds of ionizing radiation. It does kill microbes really quickly, but kind of not intuitively, it doesn't penetrate really quickly. So it's kind of the shortest wavelength, so you think it would penetrate fast, but apparently not very good penetration. Primary use, at least according to your textbook, is in medical supplies, so especially packaged medical supplies. Probably the biggest use of ionizing radiation is with using gamma rays. And this is kind of becoming more and more accepted. Where do they come from? They're emitted by radioactive elements like cobalt, what's the number? Cobalt 60. It's emitted by that. It's been kind of slow to be accepted because people see radioactive and they think, oh, this is, making the object or the food or whatever radioactive. And that's not true. Numerous studies have said that is not the case. So commonly we use this on trying to cut down on the microbial load of foods. So this has real potential for extending the shelf life of foods, especially foods that we don't cook, like fresh fruits and vegetables. So here's a really picture that kind of sticks with me a little bit. There's two groups of strawberries that were hit with gamma irradiation. And then this is what they look like, I think it was like 2 weeks later. Okay, so the group that had been irradiated, okay, I'd be willing to eat that. This other group is all moldy now, and I don't think anybody would be willing to eat that. So food that's been irradiated is supposed to have this Radura sign on it, just so people know. When food's been irradiated, it does cut down just a little bit on one of the B vitamin contents, but very safe. Some foods, it does alter the flavor a little bit. So in the US, we have kind of a list of foods that have been approved to be irradiated, and that list keeps getting bigger and bigger. Other countries, they do this in just about everything, but in our country, again, it's a little bit slower to be accepted. So again, lots of potential for foods, especially things like spinach and lettuce and things that you can't heat or you can't put chemicals on because it would have some residue. Medical supplies as well. X-rays don't have as much use. It penetrates things very well, but it takes a really long time to actually kill microbial life. So not as many applications in use there. All right. How about non-ionizing? And if you're in lab, just had a little lab work testing how well different organisms tolerate non-ionizing radiation. So ultraviolet light we've talked about this before. It creates those thymine dimers, which thymines adjacent on one strand of DNA will bind to each other rather than their complementary base pair. And that causes a lot of mutations to build up if the organism can't, if their repair mechanisms can't keep up with fixing that. Some drawbacks, doesn't penetrate very well. So we can only use this for surface, usually going to be a reduction of numbers. Usually we're not keeping it on long enough to sterilize everything. So we'll say surface sanitization. It doesn't penetrate through solids. It penetrates through liquids a little bit, through the air really well. So one application is in water treatment. So here it's kind of hard to see this, but the UV bulbs are right down there in the water. Oftentimes this is used as a final step in sewage treatment, for example, instead of dumping a bunch of chemicals in there. So you have to be really careful, regulate the water flow just right, so the UV lamps are having kind of a long enough exposure to the water, kind of a final step before it's released back out into, say, the Grand River or wherever else. Of course, UV is like gamma rays and X-rays. It's harmful to humans, so we don't want to be exposed to that. We would get sunburn. Blistering of skin has potential to cause skin cancer. Okay, that's why we use, sunblock when we're out in sunlight. But a lot of potential for liquid treatment. It's all those splash pads for kids that have kind of cropped up more in recent years. Most of those, I think they have to run underground through UV light. Some other kinds of chemical treatments aren't really is good enough as some of the fecal contaminants. We'll talk about that a little bit later. We talk about iodine. Also, just anything you want to kind of reduce microbial numbers on that it's not feasible to heat it or add some chemical. So things like goggles in the chemistry lab, hit them with some UV lights, sports equipment, things like that. So lots of potential uses. Here's just the figure from your OpenStax. I noticed here when they're showing thymine dimers, they call that a hydrogen bond, which I don't think is correct. That's just a detail, but hydrogen bonds are really just kind of attractions between different molecules. And again, the covalent bond is much stronger. So I read a little bit about that and I checked that out. I don't think that's right. Here's a application, our fume hood in microbiology lab. That's where our UV lamp is. That's because that's just another way to cut down on numbers if you're doing a lot of culture work in there, just to even better aseptic technique if you hit your surfaces with UV. Here's one more application, maybe in hospitals, kind of just one more method to maybe you had a patient in that room that had a infection with some bacteria that were resistant to a lot of different antibiotics. Maybe you wiped down every surface you can think of with some kind of disinfectant chemical, but just one more tool, wheel the lamp, the UV lamp into the room, leave the room, turn it on remotely, leave it on for like 15 minutes, turn it off remotely, come in, move it to a different spot in the room. Again, just to try to get every surface you can when it's really important, when you know you have some bacteria that's particularly dangerous. Okay, so that's it for our physical control. I have a few chemicals that I want to talk about. Over the years, I've kind of narrowed this list down just a little bit. These slides are a little bit wordy. I guess I make you write less, and I've got more words up there, maybe than what I normally do. But our society is kind of obsessed with using chemicals to cut down on bacteria and viruses. Understandable during a pandemic. Even pre-pandemic, it seemed like we were making progress there in kind of turning public opinion that we don't have to kill absolutely everything on every surface. You know, cleaners that you use at home don't have to be the same kind of cleaners that you're using at a hospital. You know, most of the microbes that you're around every day are not hurting you. People ask me a lot, you know, if I'm really crazy about cleaning at home. Honestly, I pick things up off the floor and eat them all the time at home. Like, I'm not a germaphobe. There are times where I am going to be very careful, and that's if I'm working with raw meat or if I'm cleaning up some kind of fecal contamination, some really big mess. You know, then yeah, I'm going to pull out the chemicals. Otherwise, I don't really worry about it that much. Or if I've been around somebody that I know is sick, okay, then I'm going to pull out the chemicals. But there's kind of before the pandemic was kind of a backlash that, hey, there's chemicals that we're putting in everything that don't really need to be there. Do we need an antibacterial chemical in the plastic of our TV set? No. I think we would kind of argue no. So there was kind of a backlash again pre-pandemic against that. But all right, good chemical antimicrobials. How do we choose which one to use? Ideally, it's going to have low side effects, meaning it's going to be safe for us to use kind of over and over again. Ideally, it's going to be soluble in water, as well as useful at high dilutions, because both of those things are going to make it more cheap, more inexpensive to use. So that would be ideal. And ideally, they're going to target a broad spectrum of microorganisms. Okay, what do I mean by broad spectrum? That means it's not just killing maybe bacteria, but maybe it's deactivating viruses. Maybe it's killing algae or fungus or protozoa, lots of different kinds of organisms. Okay, so there's not one perfect chemical. You have to kind of look at what you need it for, and then kind of pick out your best option. All right, so we're going to start with our what we would consider low-level disinfectants and antiseptics. Remember, disinfectants designed to be used on non-living surfaces, antiseptics on living surfaces. So by low level, I mean these are chemicals that got to work. If you remember that chart of microorganisms, the hardest ones to kill, prions, easiest ones, envelope viruses. So a low-level disinfectant is going to kill the lower ones, like the envelope viruses, maybe the gram-positive bacteria, you know, maybe up a few steps from that. A high-level disinfectant is one that kills spores. Okay, so we'll get to that. Kind of the first thing you think of when you want to maybe disinfect a surface or your hands is the use of a soap or a detergent. Okay, both of these are surfactants. Okay, that's the major ingredient in both soaps and detergents, and that just means there's chemicals in there that are going to reduce the surface tension of liquids, so it kind of decreases the attraction of microbes to dirt or dirt from that surface. Okay, what's the difference between soaps and detergents? Soaps are going to be produced from natural products. And detergents are considered synthetic. I was looking up, like, so we've had soaps for, you know, hundreds and hundreds, thousands of years. I was looking up kind of how to make soap, and you take some like animal fats and hydrogen peroxide. I don't know where they came up with that, you know, eons ago. But it's you know, things apparently that are kind of generally available. Oh, you turn, and then you have to turn the oil into a salt when you add that sodium hydroxide to it. Soaps work not because there's a chemical in soaps that actually kill microorganisms, but they are a really good degerming agent. Okay, so in other words, the surfactant in there is going to loosen up the dirt from our hands, for example, in soaps, and then we scrub it, that's degerming, and then we rinse it all away. So basically it just releases the microorganisms from the surface or your hands or whatever. Detergents, a huge class of detergents that are really commonly used are quaternary ammonias. Okay, and they work, again, they've got surfactants in them, and they are also, like soaps, going to insert into membranes. Okay, so if you look at the structure, again, not to memorize, but here's a structure of a soap. It's got a hydrophilic head and then this long hydrophobic tail. So that tail will insert into membranes, disrupt membranes. And we know that that will very quickly lead to death for microbes. Here's some structures of different quats or quaternary ammonias. Again, we've got the head and the hydrophobic tail region. Here, the little blue circles are the quaternary ammonia agents there that are inserting and disrupting a membrane of itself. Okay, what else did I want to say that? Okay, moving on, I just want to talk briefly about phenol. Phenols are really not used very much anymore. So I kind of hesitated whether to include that this semester, but we'll just include a few things about phenol. Here's the structure of phenol, get the benzene ring. This is also known as carbolic acid. Okay, and if you remember way back, I think the first day of class, we talked about Joseph Lister and how he advocated using carbolic acid for surgeons to wash their hands, and he sprayed it in the operating rooms, put it, used it pre-surgery on patients, and that did, carbolic, and that did a lot to cut down on the incidence of infection. Also was really bad for the people that were actually around it all the time. So it's really, phenol is really irritating to hands. Surgeons' fingernails dropped off, their hair fell out, it turned gray, they had respiratory problems. So we realized very quickly that maybe it's not a good idea to be around phenol all the time. Now, if you actually make a bisphenol, if you put two those benzene rings together, here's an example of two bisphenols. It actually, we tolerate them just a little bit better. They're a little bit less toxic than phenol. And don't worry about the names of these compounds. This one is called Ophenylphenol, and that used to be the active agent ingredient in Lysol. Okay, now I believe they are using an alcohol as the active ingredient, but that's changed over the years. This is called hexachlorophene, and that used to be commonly used in hospitals for surgeons to wash their hands in. It was a product called Physohex. Okay, they don't use that anymore just because it's very often, I understand, because it's, again, pretty irritating. They used to wash babies in it until they decided that it might be contributing to neurological problems. So don't use that anymore. Really, in terms of the only products that I could find that really have phenol in them, throat lozenges, which is kind of surprising. That the one brand, Chloroseptate, is that what it's called? Chloroseptate? Yeah, Chloroseptic. It's the one that you spray in your throat if your throat's really sore. It has kind of a numbing effect, so your throat doesn't hurt so much. It's only like 1.4% phenol that's in there. And actually, you're supposed to spray it in, leave it for like 15 seconds, and then you're supposed to spit it out, which I had never done when I've used that in the past. But so throat lozenges and mouthwash, some kind of really high-powered mouthwash. Of course, you're not swallowing that. You're supposed to spit that back out. Okay, so Phenol used to be kind of the gold standard of disinfectants. We have less irritating, safer options now that we primarily would turn to. Okay, so if we're moving into kind of the intermediate level, there's a whole class of halogens that are useful antimicrobials. If you kind of picture the periodic table, the halogens, of course, they're non-metal elements on the right-hand side. Their outer shell is almost full. So they are trying to grab electrons from other molecules to fill up their outer shell. Okay, so they work because they're oxidizing cellular components. So we're going to talk a little bit more about chlorine and iodine. Bromine, the application that I could think of is that this is a little bit more commonly being used in swimming pools because it's a little bit less irritating than using some kind of chlorine. It's also a little bit more expensive. And of course, fluorine, we add that to our drinking water, really, really small amounts that helps make our tooth enamel a little bit stronger, cut down on cavities. Okay, let's see, what else? Because it's an oxidizing agent, that especially is going to impact proteins, denature proteins, as well as, especially proteins. Okay, it will eventually kill endospores with a long contact time. A couple of hours is not considered kind of a reasonable amount of time, so that's why we have it in that kind of intermediate level, and rather than considering them a high level disinfectant or antiseptic. All right, so let's talk about chlorine. A lot of different applications. It's kind of when I'm disinfecting at home, that's kind of the first thing that I think of, using something with some chlorine in it. It's considered a disinfectant, not because it's bad necessarily to get it on your skin, but if you use it on your skin a lot, it would be irritating. So it's considered a disinfectant. One drawback to using chlorine, it's pretty susceptible to an organic load. So that means if you've got a mess, maybe it's a lot of dirt or it's a lot of vomit or blood or whatever, you can't just add bleach to it and wipe it up. You need to clean up that organic substance and then add bleach in order to disinfect the floor or whatever you're trying to clean up. It's also quite sensitive to light and pH, right? I mentioned this before, that if you've ever taken care of a swimming pool, you got to make sure the pH is in a certain range, or else the chlorine, whatever type of chlorine that you're using, will dissociate and not be effective anymore. In terms of light, that's why you buy bleach in these opaque containers, because again, when it's exposed to light, it will dissociate and it won't work anymore. Something that's it's been obvious to me over the years is that you can't keep your bleach for a long period of time. It actually says on the bottle to use it between 6 and 9 months, because even though it's in that opaque container, it will just start to dissociate when it gets older than like 9 months. So if you're using bleach to try to get your towels white again or whatever, and it's not working, probably because your bleach is old. So buy bleach in smaller containers, use it up, and buy more when it's done. Let's see. So there's lots of different types of chlorine. Chloramine is actually a derivative of chlorine. It's ammonia that's got a chloride group here. Chloramine is just a little bit more, it's a little bit more stable, so it works for longer. And when you add it to things, it keeps working. Like if you add it to a surface, it would keep working for longer rather than just kind of on contact. Chloramine it's not bleach mixed with ammonia. That's really bad. If you mix bleach and ammonia together, that puts off a toxic gas that can kill you. So it's really even hard to find ammonia in stores because so many cleaners have bleach in them now. So you never want to do those. But again, chloramine is a liquid that's got the two things combined, basically. Hypochlorites, this is the kind of fancy name for bleach. We used to use sodium hypochlorites in the labs to clean down the benches. We switched to ethanol just because it's kind of nice to spray it on rather than squirt it on. Chlorine dioxide gas, if you get a large space that you need to try to disinfect, then that's useful. But all of these types, all are used for various phases of kind of different kinds of water treatment as well. There is some resistance. The cysts of Cryptosporidium. So I mentioned that organism last time, that outbreak in Milwaukee where 400,000 people got diarrhea from drinking tap water. That's because this protozoa Cryptosporidium is not reliably killed by chlorine. So there's been outbreaks of that, and that's why we're kind of switching more and more to using UV light as kind of to cleaning water at our treatment plants rather than dumping a lot of I think it's sodium not sodium chloride, sodium dioxide, or I can't remember the form that the chlorine is used, but more and more switching to using the ultraviolet light. And then a few uses of iodine. Another halogen. A lot of antiseptic uses for iodine. So safe enough usually to be used on the skin, especially as wound treatments or prepping skin before surgery. It's a little bit better in organics, so it penetrates through organics a little bit better. The big disadvantage here is that it stains surfaces. So even if in lab you found that, iodine or betadine are the best disinfectants, we're not going to switch and start using that on our lab benches because that would be a mess to use that all the time. It's a little bit irritating depending on what form the iodine is used in, and some people have allergies. That's probably true for just about anything you would use. You might have heard that term tincture of iodine. Anything that's a tincture, that just means that it's dissolved in alcohol. So that's less irritating than just elemental iodine. And even less irritating is when we use iodine as an iodophore. An iodophore just means that it's linked, the iodine is linked to some kind of carrier molecule that makes it a little bit longer acting. So you put it on a surface and then it keeps disinfecting over a longer period of time rather than just kind of that contact disinfecting. So that povidone iodine, that's an iodophore, and the trade name for that is called betadine. Okay, so I just put up the structure from your book of betadine. Most of the time when we're using iodine, again, pre-needle poke or whatever, it's in the form of betadine. Okay, so lots of medical applications. This is a picture of scrubbing a hand before hand surgery. Lots of medical applications. Another application, while I was reading about, well, it's, when you Google something, you get into these wormholes, but I was reading about using iodine pills. That's big over, Russia and Middle East right now because they're worried about nuclear bombs or, problems at nuclear power plants. So you take iodine pills and that's supposed to kind of protect your thyroid against nuclear radiation. So I got to reading about that. But you can also add iodine in pill form to drinking water as sort of an emergency way to make it potable to drink and make sure there's no cryptosporidium cysts in it or whatever. The problem with that is that actually that is the problem, that it's not really strong enough to reliably kill that cryptosporidium or giardia. It does clean it mostly from other things, but it's probably best to boil water if you have access to that. Iodine maybe in a pinch. But another application, dairy applications. This is probably the cleanest cow that you will ever see in this picture here. I think typically before milking, cows are kind of hosed down a little bit. But you think about it, you want that teat clean because any dirt is going to go into the raw milk. And we have standards about how much bacteria even can be in raw milk before we pasteurize it. So it's very common to use something called teat dip, which is an iodine solution. They'll go down and kind of squirt that on all the teats. It has to have some contact time on there, so they'll kind of go down the whole row. Then they'll go down and kind of wipe that iodine off before they hook up the milking equipment. Okay. All right, another chemical still considered in that mid-range that we're using a ton right now is some form of alcohol. We use it a ton because it's very inexpensive. So usually in the form of ethyl alcohol or isopropyl alcohol. That's just what we normally call rubbing alcohol. And of course, probably a lot of you have some hand sanitizer with you right now. That's between 60 to 70% alcohol. So it can be used as an antiseptic. It can also be used as a disinfectant. Like we spray it on our benches in the lab. Depends on the concentration. It works because primarily it dissolves membranes, but also is going to denature proteins. So it works in several different ways. We mentioned earlier that usually when chemicals are more concentrated, they're going to be more effective. This is the one exception to that rule. You would think that 100% alcohol might be the way to go. Actually, a little bit of water is necessary. A little bit of dilution is necessary just for that surfactant action. Okay, so for the alcohol to dislodge microbes from whatever they're stuck to, basically. And in addition, 100% alcohol evaporates really, really quickly. So if you dilute it just a little bit, it stays around a little bit longer, so you have enough contact time. It's fairly non-irritating to the skin, although I have had some hand sanitizers that smell so bad that my nose couldn't tolerate them. It can be irritating if you breathe in the vapor. So not from hand sanitizer. That's a low enough concentration that's not going to hurt you. But if you're breathing in the vapor a lot, that is considered an inhalation hazard. By the way, you shouldn't drink hand sanitizer. It's something that you probably don't need me to tell you. But this is denatured alcohol in here, so that will give you alcohol poisoning. In addition, there's other additives to hand sanitizer that would make you ill. So you kind of hear weird things online every once in a while. Just reiterate that. Okay, so I have to mention what's better, using hand sanitizer or washing your hands with soap. Well, if you do both these things properly, you're gonna use enough hand sanitizer to moisten your hands for at least 15 seconds. Okay, so you gotta use a pretty good glob on there so it has enough contact time before it evaporates. And if you're washing your hands correctly, you want at least kind of 15 to 20 seconds of scrubbing action there. I admit I probably don't usually do it that long. Okay, so using it correctly, which is considered better? everything I've read said that washing your hands is still the best way. Although if you don't have access to soap and water, then definitely hand sanitizer is going to do some good. One drawback with using hand sanitizer is that it doesn't penetrate very well through organics. So if your hands are dirty, it's not going to do quite as good a job. And it doesn't reliably kill naked viruses. Okay, so remember, those are a little bit higher up on the susceptibility. They're a little bit harder to kill. Something like norovirus isn't going to be particularly, not reliably killed by hand sanitizer. Okay, so for those reasons, it's probably best to use soap and water whenever you have that available. But again, if it's not around, it's probably a good second option. Okay, then we're going to talk about one high-level disinfectant. Again, we consider it high level because it is sporicidal, and that is hydrogen peroxide. And from what I've read, this has been called like the closest thing we have to the ideal antimicrobial because it's inexpensive, it doesn't leave any residue. It's sporicidal only at high concentrations. So like 30–35% is considered high concentration. The kind that you buy at the drugstore would be 3%, and that's a really good antiseptic. Okay, so at low concentrations, it's used as an antiseptic. At high concentrations, as a disinfectant. It works because it forms hydroxyl radicals, which it will kind of degrade to having that unpaired electron. That's the most toxic of those toxic oxygen species that we talked about. So it's grabbing electrons, it's an oxidizing agent. A lot of damage in the cell, proteins, membranes, a lot of different kinds of damage. It's very broad spectrum. It's going to kill a lot of different kinds of organisms. It does have the disadvantage of being photosensitive. So again, that's why you buy it in these brown bottles. When it's exposed to light, it just goes off and loses its activity really rather quickly. So yes, question. What causes it to be photosensitive? Oh, man, I don't know. Good question. Anybody know? Probably has something to do with the structure, and I will look that up. Remind me if I don't get back to you on that. It's a good question. Okay. Back in the day, I know that when I would fall and skin my knee, it was really common to use hydrogen peroxide on wounds. It's kind of fallen out of favor for wound treatment because it's actually kind of harmful to our cells as well. So it will slow healing. It's fine to use it kind of like as a first time disinfectant. Just don't keep adding hydrogen peroxide to an open wound because it will slow healing and the wound will be more likely to scar. So other things like triple antibiotic ointment are a little bit more commonly used now for wound treatment anyway. Okay, any other questions? Any chemicals, anything antimicrobial? Okay, yes. Are the advantages only, I think for any whatever concentration you use, it doesn't leave residue, it's pretty safe. Broad spectrum, I guess, right, you wouldn't want to use 35% on skin. So yeah, another question. Oh. Yeah, I mean, so the question is, how effective is alcohol as a disinfectant? Would you want to pour alcohol like vodka? Now that's a different kind of alcohol, but again, I would have to research that, but it seems like that would have some use. Yeah, that's a great question. Yeah. You also see, I know there's an episode of Friends where they, well, no, that's the jellyfish one. But if you pee on a wound, like, okay, how good is that? That I read is not recommended because you actually do have some bacteria in your urine. It's not totally sterile. So I wouldn't do that unless you're really desperate. But okay, good questions, good things to think about. Okay, so let's just wrap up here by me introducing our next section. We're going to get into antibiotics on Friday, but I like to do a little, hey, public health. Let's kind of think about some public health issues first as we get into talking about antibiotics. And this is very interesting to me, this table of the top 10 things that kill us. What are the top 10 things that killed us in 1900 compared to modern age 2010? Okay, this would be a little bit different if it was today. But if you think about infectious disease, in 1900, the top causes of death were all infectious disease: pneumonia, influenza, TB, gastrointestinal infections, like things from untreated drinking water. Diphtheria is another one that made the list there. In 1900, I read that, this is astonishing to me, 1 out of 3 children died before age 5. Okay, so which is astonishing, like, and it mostly due to infectious disease. So the lifespan, the average lifespan in 1900 was 47 years. Okay, so that's not because people died when they got to be 48. It's because there was so many kids that died young that averaged out to like 47. So today, the only, pneumonia or influenza makes number 9, or at least in 2010. By far, the most common things that killed us were heart disease and cancer. So as of 1910, the life expectancy was about 74 years, and that depends if you're male or female or whatever, but about 74. So again, we've come a long way in fighting against infectious disease. We still got problems, obviously. This is not super up to date, but as of early 2021, we're back to having an infectious disease as being the #1 cause of death, at least in the US. So yeah, we got a ways to go. We are dying less often these days. The death rate is lower than what it used to be. If you look at some of the things that has contributed to that declining death rate, really hygiene is really a big thing. Back in early 1900s, we started treating our water. We started pasteurizing our milk. Of course, we have a big outlier here, that 1919 flu pandemic. But other than that, again, advances in hygiene. Here they note the last transmission of plague in the US. That was before antibiotics. We were getting clean enough and realizing that, rats are carrying the fleas that carry the bubonic plague. And again, improvements in hygiene. First use of penicillin in the 1940s, further helping us fight infectious disease. And then we had, starting kind of 1950s with the polio vaccine, lots of different vaccines that are really making infectious disease less common. A little uptake here, the late 80s, they started giving a 3rd measles booster because we were having outbreaks of measles in college campuses then, and rise of bacteria that are resistant to lots of different antibiotics, maybe a little uptick there. But we are making progress in the fight against infectious disease. Okay, so we'll start out next time talking about some terminology, a little history, and antibiotics. So have a good day.